Okay, well here we are at day 13. We're going to begin to take a look at the idea of a limit of a function. Bridging that pre-calculus gap into the arena of calculus, a derivative is a limit. So it makes sense that we study limits because a derivative is just about most of what we do in here. We do take a look at some antiderivatives near the end of the course. But for the most part, we're studying rates of change and derivatives and other applications of derivative. So since a derivative is a limit, it makes sense for us to dive into limits. And so that's what we do. It's not a real formal exploration of limits. You may have heard of a kind of an epsilon delta approach to limits. It's not one of those yet. If you look in the appendix in the back of the book, if you want something quite a bit more formal, an epsilon delta treatment of limits, then you're welcome to take a look in the appendix in the back of the book. I think the idea of limit will be conveyed by what we look at here at early chapter 2, so you won't have any reason to doubt your ability to interpret limits and what it is you've actually found once you found them. So the first thing, let's take a look at the definition of limit from a notational standpoint. What's the notation going to look like? And then we'll look at that for a variety of functions. Functions that we have a description of the y value, some split domain functions, functions that are asymptotic near a value. We want to explore what happens at or near the asymptote. So the first thing is the definition. So the notation, limit of f of x as x approaches a is L. And it says in quotes what that is, what I just read. What we're trying to do is decide what happens to the f of x values, what happens to the y values, as x is allowed to get closer and closer and closer to a, some value a that's either handed to us or we are a little suspect that the function has a problem at or near a. And then we want to see what goes on as x gets closer and closer to a from both sides. It is a two-sided limit. There is such a thing as a one-sided limit. We'll look at that today as well. But this is a two-sided limit. So if we can make the values of f of x arbitrarily close to L, as close to L as we would like, and this is where the more formal definition you'll see in the appendix, you can kind of categorize how close you want to get to it. By taking x sufficiently close to a on either side of a, but not equal to a. Now let me emphasize on that, first of all, the notation that we want to use. This notation for limit is pretty standard. We'll want to use that ourselves when we're writing down limits. And the other thing is this last little phrase right here. We don't really care what's happening at x equals a. What we're concerning ourselves with is what's happening to the function as x approaches a. In fact, the function doesn't even need to be defined at a. It may have a hole in the graph, or it may just have a point that's missing. So we don't care at x equals a. We're concerned about x near a. Let's take a look at an example. A very, very simple one. And I want to start with this one for a couple of different reasons. Let's start off with a parabola that opens up. How do you know it's a parabola that opens up? Okay. It does have an x squared term, and the coefficient of x squared is positive 2, so it opens up. Could we put this into a more standard form? Well, let's see. Does that sound familiar, by the way? Put it into a more standard form, find the vertex, and let's get a look at it. Is that the same thing we started with? Right? Factor a 2 out of the x squared and the 4x. I left some space, right, to complete the square. And then I just kind of took the negative 3 out there and sent it out there further to the right, just kind of get it out of the way. What completes the square? What makes that a trinomial that is a binomial squared. Plus 1. What did I just add? When I write in plus 1, what did I just add to the right side? Did I add 1? I really added 2, because everything inside these parentheses gets multiplied by 2. So by putting a plus 1 in there, I just added 2 to the right side. So to compensate for my addition of 2, I better also subtract 2. So we completed the square. That makes that a perfect square. So we should be able to find the vertex of this parabola by analyzing this. That means what? Go to the left 1 unit. And this little thing here at the end means we go down 5. So the vertex ought to be, if those weren't there, right? If it were just y equals 2x squared, the vertex would be at the origin. So we move the vertex from the origin left 1 and down 5. So there's the vertex. Look back at the original equation. We're not going to belabor this point, but if x is 0 in the original function, the way it's written, what's the corresponding y value? -3. So it also goes through the point 0, -3. And we would expect it to be a little skinnier, right, than y equals x squared because of the coefficient 2. Causes the y values to go up quicker, which means the net effect is it makes it a little skinnier looking. Now, is the domain of this parabola all real numbers? Can I put in anything I want to for x? Can you square anything and multiply it by 4 and double stuff? I mean, there's no reason to restrict any x's, so the domain is all reals. Now, from the picture, can you pick off the range?
-5 to infinity.
Okay, the lowest you'll ever get is -5, right? So from -5 to positive infinity, right, for the range. So we have an idea what this is. There's no suspect x values at all. Any x will do, throw it in there, do what it says to do, and you get the corresponding y. And we would expect all the y's to be -5 or larger. So if I took this function and I took the limit of the y values, what's going on with the y values as x approaches any number we choose? That ought to make sense, right? I can choose any x value because there's no holes in the graph, there's no vertical asymptotes, there's nothing strange going on. So in fact, I'll refer back to this picture, but let's take this function. I'll need some calculator help here, so if you have your calculator, get that fired up and ready. So it really doesn't matter what x value. I think I chose 1 just for simplicity's sake. So we want to know what's going on this function. Arbitrarily picked an x value, x equals 1. We're concerned with what happens as x gets closer and closer and closer to 1. What do the y values approach? So here's one approach that the authors take, which is a valid approach. Since we need to approach 1 from both sides, let's do so less than 1. And let's do so over here a little bit larger than 1. So 0, 0, 1. Thank you. So we want to get closer to 1. On the chart on the right, we're larger than 1. So you'll see this notation. It's going to be hard for me to stay away from this notation. Here we're coming in from the right. And with that little superscripted minus, that means we're coming in from the left. So if you don't see from the right or from the left, you're supposed to come in from both sides.
So why is it x versus
Negative 1. Golly. Thinking of a problem ahead where we are approaching negative 1. Yeah, x is approaching, let me clarify that. X is approaching 1 from the left. X is approaching 1 from the right. Thank you. Just kind of keep on your toes today. I'm struggling, so I'll need some help. So here's where I certainly need some calculator help. Somebody throw in that value for x, 0.9, and do what it says to do here and see what you get. Somebody else plug in 0.99 for x, and somebody take on 0.999 for x and see what you get. Okay, anybody run 0.99 through that function?
2.92.
2.92?
Yeah.
How about 0.999? Somebody run that through your calculator and see what you get.
2.99.
Okay. All right, let's see if we can spread this out. Somebody plug in. Now we're going from the other side of 1, a little bit larger than 1, 1.1, 1.01, and 1.001. Just pick one of those three and run it through your calculator. How about 1.1? Anybody got that one?
2.61.
1.01 into that function.
$2.06. Is that right?
I think it's
3.08.
For the first one, I got 3.82.
Okay, I'm somewhat dubious of that right now. 3.82?
3.08.
Got
Yeah,
some agreement on
82.
that?
82, yeah.
And
3.82. And 3.01. Now, as we're getting pretty darn close to 1, what does it appear that the y values are getting closer to?
3.
Looks like 3. Now, do you foresee a problem when you have a function like this? I know we're not supposed to let x be 1. We're supposed to let x approach 1. Do you see a problem with letting x actually take on the value 1 and see what we get? Does it appear that we're approaching the value that we actually, in fact, get to when x is 1? So if it's a nice polynomial function, which this is, there's never a problem with just kind of plugging in the value that we're approaching and seeing what you get. So it appears certainly that we're getting closer and closer to the y value 3 from either side of the x value 1. Now let's go back to the graph. Let me actually make the graph a little larger than my initial graph. We know that as x is approaching 1, from this side we were a little less than 3, and from this side we were a little larger than 3. We have every idea that if we get even closer and kind of pinch in and move in on 1, that we're going to get closer to 3 and closer to 3. And in fact, at 1, you would get exactly the x value 3. And that's not out of line with what we thought, right? So the picture is that we're coming in from this direction, and we're also coming in from this direction. And if it's a nice, clean polynomial like this, we're converging on the same value from both sides. That's what we want to happen when we evaluate a limit. So the answer to that limit is 3. Now, if this gives you a little problem that we said we're just going to plug in 1 and do what it says to do and we get 3, again, we're not really concerned what happens when x is 1 We're concerned with when x is approaching 1. So is it okay to say that the limit is 3? That's a limiting value. We're approaching 3. Again, we don't care what happens at x equals 1, per se. We want to know what happens as x approaches 1. So if it's a polynomial, those are usually the easy ones. Let's look at a split domain function. It's kind of a unique picture. So we want x to be that rational function, or at least it looks fairly rational. That's the y value when x is not 2. In fact, I don't really need to say x is not 2 because x can't be 2 in that one. And the y value is 5 when x is 2. Anybody know what that first one is, that first line?
Is it x plus 2?
X plus 2.
X plus 2. Because x is never going to be 2, right?
Mm-hmm.
So I could factor the top. And you cannot always cancel x minus 2 over itself, but it's certainly legal to cancel x minus 2 over itself as long as we can be sure that we're not canceling 0 over 0, right? We're not. We're not, because x is not 2. So it's permissible to reduce those. And we're left with that. Umair.
Sir, I don't understand that part. Like when x is equal to 2, y is 5.
That's just the second part of this split domain function. So we're analyzing right now the first line. We'll get to that, okay? But the first line is the y values are defined by x squared minus 4 over x minus 2. As long as x is not 2, we can reduce those like factors, numerator and denominator. Now what is, and we'll get back to the question, but what is y equals x plus 2? If you graph that, that's a line. Now do we want the whole line?
No.
Okay, we can't plot the point when x is 2, right? According to what we were handed. We cannot let x be 2. And this isn't the finished graph. This is the graph of the first piece of this. What is that? Y-intercept 2 and a slope of 1. So would you describe that first line as the first piece of this split domain function? Would you say that it was accurately described as a line with a hole in it? Is that right? X can't be 2? Now, why is there not a vertical asymptote there? I thought when something was undefined at a number, it kind of was crazy when you were close to that number. Like if it's undefined at 2, shouldn't it be kind of distorted near 2? Does that create a problem? Let's suppose x is 2.00001. Is that a problem? That doesn't cause anything to go crazy, does it? In fact, can I still not reduce this? If x is 2.00001, does that number minus 2 over that same number minus 2, doesn't that always reduce? Except for when it's 0 over 0, right? So it doesn't distort near 2. It's just got a bad value at 2. So it's going along nice and smoothly, nice linear, and then we just kind of take a little intermission there at x equals 2, and then we pick right up on the other side. So it is a line with a hole in it, and now we get back to Umair's question. The y value is 5. When? Not very often.
When x equals 2?
Oh, the only time the y value is 5 is when x is 2. So isn't that the point 2, 5, right? When x is 2, y is 5, end of that story. So we come back and plot that point. So is this a function? It is a function because we only have one point plotted when x is 2, and it's taken care of everywhere else. So it may not look like a line with a hole in it with some other external point plotted, but that's exactly what the original set is. Now here's the problem I want us to consider. What's the limit of this function, of the y values, as x gets closer and closer and closer to 2, what do the y values get closer and closer to? 4? How many of you think 4? I do. Let's see. On the picture, we're getting closer and closer to the x value 2. Closer and closer to the x value 2. What is the y value getting closer and closer to? 4, right? Now, how do you know 4? You could look back at this line that has a hole in it, and say, okay, I know I'm not supposed to use x equal 2, but let me just kind of off to the side see what happens if x were 2. If x were 2, what would y be?
4.
It'd be 4. So that's the point we deleted in the original set. We deleted the point 2 comma 4. And now we know that that's the y value that we're getting closer and closer to as x approaches 2. Now, does it really matter that I plotted the point 2 comma 5? Does not matter.
So that doesn't do anything?
We could have left it out completely, or we could, it could be 2.5, it could be 2.7, it could be 2.4. Right? We could fill in the hole from the first part of the graph, and it doesn't matter. It doesn't matter what happens when x is 2, and that's why I chose this example, is to get us to not look at what happens at the value, but rather what happens as x approaches the value. So on this problem, what is the limit of the function as x approaches 2? The answer is 4. We're getting closer and closer to the y value 4 as the x gets closer and closer to 2. Doesn't matter what happens when x is 2, it matters what happens when x is approaching 2. And I can tell from your expressions you just love split domain functions. I have another one for you here in a minute. Let's off to the side before we get to a split domain function. Let's look at this guy. Guess where we're going to look at this? Where is the point that you would be highly suspect of this function maybe possibly misbehaving?
2.
X equals 2, right? We know it's completely undefined at x equals 2, but it's undefined in a different fashion than the previous problem. Don't you recognize that as having a vertical asymptote, right? Here's one that gets weird near 2, right? When you put in that value, and when you put in that value, it kind of begins to get weird near 2, and it's very, very weird at 2. I think we all agree it's very weird at 2. In fact, it doesn't even exist. What happens if I would put in 2.0001? What do you get? Well, the denominator is 0.0001, right? 5 divided by that.
5,000.
So it's
50,000.
5 multiplied by the reciprocal of that. 5,000? Is that right?
50,000.
50,000? Pretty large positive number. So near 2, this thing has a problem. At 2, clearly it has a problem. So from the right side, it looks like we're way up here, right? Let me use a different color here. Does that seem right? That it's approaching positive infinity from the right? How about 1.999?
Negative.
Negative 50,000? So it looks like not only is it strange at 2, it basically doesn't exist. It's becoming strange as we get closer to 2, which the previous graph did not do. So the question is, since we're talking about limits, does this have an answer? What happens to the y values on this function as we allow x to get closer and closer and closer to 2? Well, from one side, we're going up to positive infinity. From the other side, we're going down to negative infinity. Are we closing in on the same number from both sides? We absolutely are not. You can't get any more opposed than what we're doing on this graph. So we'll say it does not exist. Or you could say, no, there is no limit. Now, would things be any better if we were approaching the same side of infinity? Let's say the graph were going way up to positive infinity on both sides. Would that help the cause? Not really, because are we approaching any one specific number? No, positive infinity is not a specific number. So you've got to be closing in on the same exact number from both sides. It's going to infinity, all you have to do is say it doesn't exist. There is not a limit with an emphasis on the word a, meaning 1, right? There's not a one single number that we're approaching from both sides. So we're going to look at today one-sided limits. So let's go ahead and get that started right now. So we just had this picture. And on one side we had this thing coming up here, and on the other side we had it coming down here. So let's come in from the right. So we're coming in, here we are from the right, so with numbers larger than 2. I don't think descriptively there's a problem with saying that we're approaching positive infinity, but positive infinity I don't believe is ever an answer to a limit problem. So if you don't have a single number that you're approaching, I think it's best to say there is not a limit. It does not exist. Other side, coming in from the left, again, no limit or does not exist. So if you can't give a single number for an answer, then there isn't an answer. Questions on that? Anybody? Now, occasionally you'll see that the answer to this will be positive infinity and negative infinity. I don't have an extreme problem with that if it's for descriptive purposes. You're saying what happens to the graph. The graph blows up to positive infinity, the graph goes down to negative infinity, but for an exact answer to a limit question, I don't think we need to give that as an answer. Okay, here's kind of a unique one that we'll visit today and then we'll revisit it later. Sine of x over x. If you were to graph sine of x over x is in radians now. You would see that it looks something like this. So obviously it's not defined at 0, but as you get close to 0, believe it or not, this thing is pretty well defined. Now let me show you some things about this. Let's say that, let's just come in from the right side. It's numerically the same from the left as well, because we're closing in on the same value. I haven't told you what the value that is, but I want us to figure out from this table. Let's start out here. That's not very close to 0, I know that, but we'll get closer to 0 as we go down the line here. Pi over 6, well, pi over 6 as a decimal, that's the number pi divided by 6. Somebody do that for me. 5, 2,
0.523.
0.5,
0.523 or 524.
24.
Yeah.
Okay. So a little bit over a half, right?
Mm-hmm.
What's the sign of pi over 6?
1/2.
It's exactly 1/2, right? So we're not very close to 0 yet, and the sign of x is pretty darn close to the x value itself. Let's keep going. Pi over 12, which would be the degree, or the equivalent of 15 degrees. What's the number pi divided by 12?
0.262.
Okay? And what's the sign of pi over 12? 2.588, is that right? It's equivalent of the sine of 15 degrees, 0.2588. Pretty close together? The value of x and the sine of x. Okay, let's skip down here a little bit. Put in 0.1 radians. What's the sine of 0.1?
0.099.
Pretty darn close to 0.1, right? Very, very close to 0.1. Let's do one more. 0.01. What do you think is going to be the answer? Pretty close to 0.01. So as you get closer to 0, the value you plug in for x is the same as the value, for the most part, that you get from the sine of x. Somebody want to give me that?
0.00999.
Is that pretty close to 0.01? Very, very close. So doesn't it appear to you that these values of x and the sine of x are getting closer together as we go down this table, as x is approaching 0? So tell me, what is the answer to this?
1.
It's 1. So as x gets closer and closer to 0, the sine of x and the value of x are getting closer and closer together. Well, what is something over itself? It's 1. So this limiting value is in fact 1. It's 1 from this side. We just basically looked at that. If we came in from the other side, it would also be 1. Now it's completely undefined at 0, but near 0, sine of x and x are practically the same. And we'll have other ways that we can examine that problem later on. Okay, one last problem, and that is a split domain function. Any question with this?
Hold on.
Yes.
You said as it approaches 0,
Yes.
it does what now?
That the value of x and the sine of that x value are getting closer and closer together. So anything over itself is going to be 1. So it really doesn't matter, and since we wanted to revisit, it doesn't matter if this is sine of x over x or x over the sine of x. Same answer? Same answer. The numerator and denominator are getting closer to one another, therefore we're getting closer and closer to the value 1. Is that okay? Okay, the split domain function. And then I want to look at some one-sided limits that actually exist here. So we got a little piece of a parabola. I think this is why I chose -1 a minute ago. At least we'll use that for an excuse. So it looks like it's part of a parabola for a while and part of a line for a while. And it looks like where that transition takes place is, well, you tell me. Where does it transition from a line to a parabola?
-1.
At -1. So we'll take the first line, and I have to remember that I can only put in values greater than or equal to -1. The second line of my split domain function, I can only put in values less than -1. So where do I have to start?
-0.99.
Okay, that's exactly right. I can be very, very close to -1, right? I don't have to skip back to the following integer. I can be how close to -1? Here's what I like to do on these. I like to be so close to -1 that I actually put in -1. That's pretty close, isn't it?
Mm-hmm.
But then I make a little note to myself that this point doesn't quite make it to this set, right? I can't legally use -1, but I can come right up to this point, and that will become my open circle. I'm going to delete that point. All right, let's fill in some of these things. If x is -1, what do we get?
Five.
Well, we
Positive.
square
yeah.
-1, which is 1, and negate that, which is -1, plus 4. 3, 0, 4, 1, 3. So I think we've got the little downward turn of our parabola. And 2, 0, okay? And we can keep going with that. Choose any value greater than or equal to -1. If x could be -1 in this function, what would the y value be?
-4. I know.
Negative 2? So that's the point we delete. We come up to that point and don't include it. And again, I have to use values less than -1. And it's linear, so we can just put in a couple. 3 is plenty. If x takes on the value -2, what do we get?
-1.
-1?
Mm-hmm.
And if x takes on -3, which is legal for it to do? 0? All right, let's see what our graph looks like. Putting some of these things together. So -1, 3. That gets plotted. 0, 4, 1, 3. And then we continue, right? I can put in any other value I want to. 2 is 0. Over here on the left of -1, -1, -2 doesn't quite make it to this set. That's my open circle. -2, -1 makes it to the set. -3, 0 makes it to the set. And it's linear. Everybody comfortable with those two pieces of this function? Is it a function? I just called it a function. I guess we better validate that.
Yeah.
It is, right? No 2 points in the same vertical lines. Close. Close to not being a function, but it is a function. So there's our picture. Let's take a look at what happens, and you know what value we're going to choose. Let's choose -1. Let's come in from the right. and come in from the left. So here are one-sided limits. So from the right, as we come in, here we are on the right side of the picture. What is the y value approaching as x approaches -1? 3? In fact, it actually gets there, doesn't it? But that's not part of our concern. We want to know what are we getting closer to as x gets closer and closer to -1. Here's our target x value, -1. And now come in on the other side, so we're on the linear piece this time. What is the y value approaching as x approaches -1 from the left? -2. So we do have answers this time based on the two different pieces that we have. We have answers to the two one-sided limit questions. If these two happen to be the same, well, they're not the same. So what do I say is the answer to that?
I have another question.
Okay. Go ahead with your question and I'll re-ask that one.
If the answer is 0, do we say no limit or that limit's 0?
0. Yeah, 0 is a value that we can actually approach. The only time that you really have to say it doesn't exist is because it's either going to infinity. Anytime it's not going to any one specific number, you have to say no limit or does not exist. What do you, now let me ask this question again. What do you think is the answer to the two-sided limit question? We got answers to the one-sided limits. But what do you think must be true in order for there to be an answer for the two-sided limit? This means coming in from both sides, right? That's a two-sided limit. So are we approaching one specific number from both sides? We are not. And when we don't get one specific number from both sides, what do we need to say?
Does not exist.
No limit. Or does not exist. So there's a little definition in the book that says this. You've got to be able to get the same number from the two one-sided limits in order for there to be an answer to the two-sided limit. So you've got to be approaching the same number from both sides. Since we got 3 on one side, -2 on the other, the answer to the two-sided limit is that there isn't an answer. It does not exist. Now, every time that you have a split domain function, is this going to be true? Well, is there a way, and we'll backtrack here and then finish with this, is there a way that I could make this piece of the parabola come down here and start down here?
Shift it.
Just shift it, right? So could I come up with a function? Here's the original function. I want to keep the line piece where it is, and I want to bring the parabolic piece down so that it fills in the hole that was left out of the linear piece.
Mm-hmm.
So right now everything is shifted up 4 units. Well, here's what I'd like to do is bring this thing down so that it comes down there and actually includes that point.
-1.
Negative x squared
-1.
minus 1.
Mhm.
So if this were our function, negative x squared minus 1. What was this? Negative x minus 3? Is that right?
Mm-hmm.
Yeah.
Let me get back to my original here. That is a split domain function. It's part of a parabola, part of a line. Negative 1 is still kind of the jumping off point here. Where were we down there? Negative 2. This was the linear piece. And now we're going to include that point. So I brought that parabolic loop down. And now as we analyze the limit of this new function, now there is an answer to the two-sided limit. Why? Because the one-sided limit answers are the same. What are we approaching here?
Negative.
Negative 2. What are we approaching here? Negative 2. So just because it's a split domain does not indicate that you'll never have the answer to the two-sided limit question, but you've got to be approaching the same value from both sides. Okay, I picked out a few problems from page 108 that I think it would be to your advantage to look at. Three, 5, and 6. 9, 13, and 18. And any of those that you have a question, we can start with that tomorrow. That concludes day 13.